challenges and attack the problems. So the first speaker of this morning is Professor Séré, also from the same university, Université Dauphine from Paris. He will talk about construction of the self-consistent Dirac vacuum in electromagnetic fields, please. Thank you.
So, yeah, seems to work. So first of all, I would like to thank the organizers for inviting me in this wonderful place. The subject I would like to talk about is the construction of the self-consistent Dirac vacuum, or Dirac-C, in presence of an electromagnetic field. What I will call electromagnetic field, it will be a classical electromagnetic field. So only the Dirac-C of electrons and positrons will be quantized. And this is joint work with Philippe Graveja, Christian Heinzel, and Mathieu Lévin, which you can find as a preprint with this reference. In fact, this work is part of an ongoing program that I started a few years ago about the Dirac-C. There have been many contributions on this program. I will not list all of them. I just would like to say that all these contributions are deal with the Dirac-C in presence of an electrostatic field. Or perhaps there was also the inclusion of electromagnetic field at the beginning in a work by Barbarou had first hidden top, but without considering the vacuum polarization effect. So this is the first work where at the same time you have vacuum polarization effects and electromagnetic field. Okay, so let me start from the beginning. So the beginning of the story is the 3 Dirac operator. I suppose all of you know it, but I would like to fix the notations. So for us, the speed of light equals 1. The Planck constant also equals 1, so that you have a 3 Dirac operator which takes this form. So this is the first order differential part. The partial derivatives are multiplied by the classical alpha k matrices, and then there is the mass. The only parameter here is the mass of the electron, which is m, and which is multiplied by a matrix beta. So as is well known, these matrices alpha k and beta are 4x4 self-adjoint matrices which satisfy anti-commutation relations. These anti-commutation relations are here to ensure that the square of the Dirac operator is equal to minus Laplacian plus m squared, that is to the part of the Klein-Gordon operator. Now from this it is clear that the spectrum of dm0, the Dirac operator, should be included in the union of these two intervals, which correspond to the square roots of the spectrum of minus Laplacian plus m squared. And in fact, by going into the Fourier domain, it turns out that the spectrum of dm0 is exactly the union of these two intervals. Now, as everybody knows, if one interprets the Dirac operator as a Hamiltonian, then its spectrum should be interpreted as allowed energies of the free electron. The problem is, how do you interpret these negative energies which are never observed in practice? Dirac's solution to this question was the following. He stated that all the states of negative energy are occupied in the vacuum by virtual electrons, and since these virtual electrons occupy all the negative energy states. And since electrons are fermions, if you add a real electron in the system, it has to have a positive energy. That's why we only observe positive energy electrons. Now, the question, of course, if you have all these virtual electrons, the question is, does the presence of these electrons create some physical effect? The answer is no, as long as you don't introduce an electromagnetic field, because the states, the electronic states are translation invariant if you have no interaction, and so there is no variation in the density of charge of this Dirac sea. But when you introduce an external field, then these virtual electrons are going to react, and they are going to move depending on the external field, and that creates a phenomenon which is called vacuum polarization. That is, the vacuum will no longer have a zero charge density. Now, an additional prediction of Dirac is that if you introduce a very strong external field, or if you introduce, say, an electromagnetic wave of sufficiently high frequency, then you can have creation of electron-positron pairs. What is an electron-positron pair? Where it corresponds to a virtual electron which absorbs a photon. Say you have an incident photon here, a photon of energy which is at least twice the rest mass energy of the electrons. And then if this is minus m and this is m, this is the spectrum of the 3 Dirac operator, then this virtual electron jumps here in the positive continuum. It leaves a hole, and the hole is interpreted as a positron. So that's what you see here. Here you have the hole, the positron, after absorption of the photon. And here you have the electron, which is the particle with positive energy. Okay, so now we are going to write down a model which takes this into account. So consider a classical electromagnetic field. So I write capital A for the 4 vector, which has 4 components. The first component is the electric field potential V, and then normal A, which represents the magnetic part of the vector potential. This electromagnetic field, to this electromagnetic field is associated a Dirac operator, which takes this form. So here you add A to the partial derivatives, and you add V to the constant part. E represents the charge of the electron. And so what you call a Dirac sea is going to be a one-body density matrix acting on the space of wave functions on which the Dirac operator acts, that is square integrable functions defined on space and with values in C4. And now in its ground state, gamma, the Dirac sea, will be the spectral projector associated to the negative spectrum of the Dirac operator with potential. Okay, that's what is called the polarized Dirac sea. Okay, so now what we would like to do is the following. When you have a polarized Dirac sea, you know that, as I told you, the virtual electrons are going to move, and so they are going to create a new electric field and also a new magnetic field. And this electric and magnetic field are going to introduce a correction to the external electromagnetic field. And so, in fact, you have self-consistent equations. That is, the electromagnetic field creates a Dirac sea, and the Dirac sea modifies the electromagnetic field. So you have to write the correct equations for this self-consistent problem. So what we are going to do, we are going to derive these equations and also their solutions from a Lagrangian action. Okay, so let us write an action for this problem. And also something I would like to say in this talk, we are only considering the static problem. Of course, one could also consider the evolution problem, but well, it's already difficult enough in the static case, so I'm only talking about static polarized Dirac seas here. Okay, so here is the action. The action at a formal level, because as we will see, there are plenty of reasons why this action is infinite and has to be renormalized. So as I told you, our variables are a one-body density matrix, which is an operator between which is self-adjoint and which is non-negative and smaller than or equal to the identity. And our second, and this density matrix represents the density matrix of the virtual electrons. And then the second variable is a classical electromagnetic field, bold A equal VA. Now the formal action of this couple of variables, if you add an external field, an external electromagnetic field, this virtual action is the following. So maybe let me start with the end, which is the easiest, the most classical thing. The second line of this action is just the action, the classical action of the electromagnetic field. Okay, so curl of A squared minus grade V squared. That's the action in the context of a static electromagnetic field. Curl of A, of course, will correspond to the magnetic field, and grad V will correspond to the electric field. And now, second thing, here is the action of the Dirac sea, the Dirac sea gamma, in presence of this electromagnetic field, which is equal to the external field plus A, which is the electromagnetic field which will later be generated by gamma. Okay, so it's just the trace. What does this expression mean? Well, the thing is that in the case when gamma is the negative spectral projector of dA, okay, then in fact gamma minus a half is going to be 1/2 the negative projector minus 1/2 the positive spectral projector. Okay, and so in this case, when gamma equals the Dirac sea, what we want, in fact, when you write the trace of D A gamma minus a half, okay, well, what you will get is in fact minus a half trace of the absolute value of dA. Okay, because you count the positive spectrum of dA with a minus sign, and you count the negative spectrum with a plus sign. Okay, so that's what you will get. Okay, that's the reason why here in this line we get a reduced or an effective action by replacing gamma with the Dirac sea, which was already mentioned before. Okay, so this becomes the trace of the absolute value of D. So it means you sum up the positive energies with a plus sign, and you sum up the negative energies with a minus sign in front of them. Okay? Okay, so that's going to be our effective action. Of course, this effective action now only depends on the electromagnetic field. And this effective action, there is no way you can minimize it, because you see there is a minus gradient v square. You cannot maximize it either, because there is this curl a squared. And so the only hope we have is to look for a saddle point of this effective action. So that's what we are going to do. Yes?
Are you supposing that v is small or something?
Yes, so in the end it will appear that we are going to assume that the external field is small enough in a certain norm. Otherwise we cannot we cannot find a saddle point.
Because when you define the trace, you are assuming that you have a gap around 0. But
that's right. Yes, that's an implicit assumption. But here I was so formal that I didn't mention it, but it will come later. Yes, yes. To have a clear separation between the states, we assume that when we consider dA, here maybe we have eigenstates here, but not near 0. Okay, no spectrum. Maybe it's possible to do something when you have a spectrum near 0, but we are not able to do it. Okay, so as you can see, the problem with the definition of this formal action is that, of course, this operator has an infinite trace. So of course, written in this way, our formal action has absolutely no meaning. Now you can try to give a meaning to it by saying, okay, I have a reference situation, which is a situation when there is no external field and no generated field A. And so I'm going to subtract the absolute value of the free Dirac operator, which corresponds to this situation. And now I hope that the difference will be a trace class operator. Now the bad news is that it doesn't work. The difference is not trace class. Okay, and so this is a well-known problem in quantum field theory. People who have been working on QED in the 40s and 50s had many. They were working on perturbative quantum field theory, of course, and they found many integrals which were divergent. And now to make them convergent, you need some kind of ultraviolet regularization. Okay, so in fact, we haven't tried to be original. We have been looking through the literature to find the ultraviolet regularization which was most suitable to our problem. So of course, there is a very naive one which sometimes works, which consists in replacing the full space of spinors, of square integrable spinors, by the space of spinors whose Fourier transform has support in a ball of radius lambda. That is, you just get rid of the momenta bigger than lambda in norm. Okay, and lambda is what is called your ultraviolet cutoff. Now this prescription works very well when one is dealing with the electrostatic field, and that's this regularization which was used in the previous works I mentioned. But when you have to deal with the magnetic field, there is an additional difficulty which was already encountered in the 40s by physicists. The problem is that when you try to write down the vacuum approximation, the vacuum polarization, even to first order, you find a divergent integral which diverges quadratically. Now this quadratic divergence should not be there because the corresponding term is not gauge invariant. And you should have gauge invariance, of course, when you are dealing with a problem involving the electromagnetic field. Now you see this ultraviolet cutoff here is not gauge invariant because gauge invariance corresponds to allowing multiplication of the wave function psi by a phase which varies with position. Okay, and when you multiply f by a phase, then you see that if I call h lambda, suppose that f belongs to h lambda, then when you multiply it with a phase, it's no longer in h lambda because in Fourier space, this product has become a convolution product. Okay, and now the consequence of that is that when you make the computation of vacuum polarization to first order, you find the famous nasty quadratically divergent term. Okay, so this is to be forgotten. It doesn't work when you are dealing with the electromagnetic field. And this problem was not encountered at all in the electrostatic case. Okay, so we had to go through the literature, and in fact, the most successful method of regularization in the beginning of quantum electrodynamics is what is called the Pauli-Villars regularization. What is this regularization? Well, it consists in you see, we already subtracted dm0 from dma. But now we are going to do something more. We are going to subtract from the original dmea, we are going to subtract other operators of this form with other masses. And these other masses are going to be much bigger. So the idea is that you subtract contributions which are due to particles with very high masses. Since these particles have very high masses, in fact, at ordinary energy scales, you should not see them, but they are going to help killing the high frequency divergences. Okay, so instead of having just dm minus dm0, I have a linear combination of objects like that with coefficients Cj. Now, the coefficient j equals 0 corresponds to our physical field. So, for j equals 0, you have m, the mass of the electron, and you have the coefficient 1. Okay? And now the other coefficients describe fictitious particles. The masses mj for j bigger than 1 are very, very large. And in fact, it turns out that in our case, we only need two conditions to be fulfilled by these coefficients and masses. We need the sum of the Cj to be 0, and the second moment, the sum of the Cj mj square to be 0. Okay? That's because I don't have time to give the details, but that's because the integrals which appear when you try to compute vacuum polarization, when you try to compute, say, this integral in powers as a perturbative series in powers of E, it turns out that the first terms are integrals of rational functions which don't have the right degree to converge. Okay, but if you make combinations and if you have these conditions, then you get new rational functions which give you convergent integrals. Okay, and now this way of regularizing is gauge invariant because you just combine gauge invariant problems. Okay, so as you see, there are only two conditions. And so, in fact, I only need two additional masses. So I just need capital J to be equal to 2 in my case. That's what is explained here. Probably there has been a problem. Okay. Anyway, this condition here, by condition I mean condition 4. Okay. So condition 4 is fulfilled when you have two additional distinct masses, and in fact, for any value of the masses m1, m2, the coefficients are easily computed. Now, if I consider the case where m0 is the mass of the electron, m1 is bigger, m2 is bigger, then the first coefficient is negative and the second one is positive. Now, if you are familiar with what was done in the case of electrostatic fields, there was the Dirac sea, the vacuum polarization of the Dirac sea involved a logarithmic divergence. This logarithmic divergence, we still have it. We just killed the quadratic one. And in fact, it turns out that in the computation, you're going to find a quantity which diverges in logarithm of a certain quantity lambda, and this quantity lambda is obtained as a combination of its logarithm is a combination of the logarithm of the masses. So that's the expression you get for lambda. So this lambda, this ultraviolet cutoff lambda, is really the analog of what you would have if you chose this naive cutoff. Okay, that's the equivalent high frequency, high momentum cutoff. Now you see we have two parameters, m1, m2, and so there is a certain freedom. What we can do, for instance, we can let m2 go to infinity, and still we have a reasonable model, but we cannot let m1 go to infinity because we need lambda to remain finite. Okay, so now that we have this regularization, we are going to define a polyvillars regulated action for the fermionic, the electron-positron part, which is just the 1/2 the trace of the combinations of these absolute difference of absolute values. Okay, and what we want to do, we want to define this polyvillars regulated action for A, for potential A, living in a space which is the natural space for the electromagnetic field. That is, you consider couples VA, which are in L6. A should have zero divergence. That's the Coulomb gauge. We work in Coulomb gauge from now on. And we also ask that the electromagnetic field, so gradient V and curl A, should be in L2. Okay, so we endow our space of electromagnetic fields with a norm, which is a kind of H1 norm. Okay, so it only involves the L2 norm of the derivatives, in fact. And now we want to define Fp in this space, and we want it to be continuous and even of class C2 for this norm. Okay, so we proceed in 2 times. First of all, we are going to restrict to electromagnetic fields which are, in addition to being in our Hilbert space HDiv, they are also in L1. So we restrict to such electromagnetic fields. In this case, if A is in L1, then the operator TA, which is the operator, the trace of which we want to take, well, this operator TA is going to be trace class, so it's wonderful. We have a trace, okay? And in fact, we really need all these coefficients. If we don't have them, we don't have a trace class operator. We really need to make this cancellation process. Okay, then it's very easy to define the polyvillars regulated action as the trace of. Oh, by the way, I said a mistake. TA is not trace class. I'm sorry. TA is not trace class. You have to realize that TA acts on 4 spinors. That is, it acts on functions with values in C4. So when you write the integral kernel of TA, it's in fact, so TA applied to a wave function is going to be an integral of an integral kernel which I still write as TA times psi of y. Okay. Now psi lives in C4, and so TA is going to be a 4x4 matrix. Okay. Okay. So in fact, TA itself is not trace class, but you can define a new operator just by taking the trace in C4 of each coefficient here of the integral kernel. And this new operator is trace class, but TA itself is not. So take trace C4 of TA, okay, and you get a trace class operator. And so you can define your polyvillars regulated action as a trace of this operator. Okay. Now that's only when A is in L1, but it turns out that in practice, interesting electromagnetic potentials are not in L1. It also turns out that when we try to find the solution of our Euler-Lagrange equation, they are not in L1. Okay, and so it is absolutely necessary to extend the definition of the polyvillars action to the space H-div of electromagnetic potentials, which I remind you are not at all in L1. They are only in L6. Okay, and their gradient, well, their curl and the gradient of V and the curl of A are in L2. Okay, so we do that by taking this energy, expanding this energy in powers of the charge of the electron. Okay, and now you get, in fact, the charge of the electron is hidden here. It is absorbed in the definition of A, but it doesn't matter. So you expand in powers of A, say, and what you find is when you expand this in powers of A, you find a first term which is quadratic, which we call F2, and a remainder which starts at 4th order. Okay, only even orders appear, in fact, here. So when you take the remainder, there is no difficulty with, well, it's not completely true, but there are less difficulties with the remainder. The majorities of the difficulties are here in F2, in the second order term, which is really the term where divergences are. So what we do is that we write explicitly F2, and we find that you can extend F2 to a quadratic form defined on the space H-div. And now for the remainder, the 4th order term also created a lot of problems. We had to work a lot on it. But then the 6th, from 6th order on, it's very easy. You have no problem in the definition of the potential because of the polyvillars action, because as you see, you have the power 6 here, and that corresponds to the fact that A is in L6. Okay, A being in L6, it's okay. Here you have more work to do, and here it's even worse. Okay, so in the end, we have a polyvillars action which is no longer defined as a trace, is defined as an extension of an operator which was a trace. Okay. So now let me give you more details on this second order operator. So the quadratic form F2 can be written explicitly in this form. So you see it depends on the vector potential only through the electrostatic and magnetic fields. Okay, and that corresponds to the fact that we have a gauge invariant problem. So we should have a dependence only on gauge invariant quantities, which are, of course, the physical quantities EB. Okay, so this action, well, it's a quadratic form which is reminiscent of the classical electromagnetic action. You also have a difference of squares. Okay, but this is only in the Fourier domain. Because you have this multiplication in the Fourier domain by a function m of k. So in the direct space, you would have a convolution product. And now, this function m of k is explicit. It takes this form. Okay. Here you have the coefficient Cj, the mass is mj. Now, one can analyze very easily this function and see that it is a positive function with a uniform estimate. So in fact, m of k decays between 0 and infinity. At infinity, it converges to 0, and here at 0, it takes this value, which is logarithmically divergent. So you see why we had to keep a finite value at least of m1. That's because we needed a finite value for m of 0. And lambda was defined previously. Here there has been a problem. It was defined previously here. Okay. Okay. So that's for F2. Now, if we put everything together, and if we restrict to the case when there is no external field, so we consider the free vacuum. So what we are going to do here is to write the whole action for the free vacuum, and we are going to see that the free vacuum is stable in some sense. So in absence of an external field, you get the following effective action. So that's the classical electromagnetic action, and that's the action of the Pauli-Villars action of the electron-positron field, where now I have put again the charge of the electron, which was hidden up to now. So here you have the quadratic form, and here you have the remainder, which is 4th order, 6th order, and so on. Now, the theorem is that if you work in the space H.div, I already defined, the four potential A equals 0, that is the solution without any field, is a saddle point of the reduced action, of the effective action. And by this I mean it is a unique solution of the following min-max problem. So so 0, 0 is a maximizer of L when you let the electrostatic potential vary in a ball. So in fact it's a local min-max problem, you see. And also it's a minimizer when you fix the electrostatic field at 0 but let the magnetic field vary. Once again, you let it vary only in a ball. And the radius of this ball, is fixed. I don't give you the value because it's not very beautiful, but it's fixed as long as these numbers remain bounded. That is the charge of the electron and also this quantity which involves the masses and the coefficients of the renormalization. But you see, of the cutoff. But you see, this is really not a big deal because we have seen that the mj's are very large, so m0 divided by mj is very small, and the cj's are bounded. So when lambda goes to infinity, there is no problem with this quantity. Okay, so we have a local saddle point. Okay, and here is another way of writing it as a min sup or a max inf. That's the classical theory of min max of saddle points in convex analysis. Okay, now what happens when you add an external field? So to answer Maria's question of the beginning, we need a small external field. Why? Well, that's because, as I said here, we only have a local saddle point. So the idea is you have a local saddle point when the external field is 0. Well, if you add a small external field, you still have a saddle point. Okay, but you cannot add an external field which would be too strong because then you would get out of the domain of the initial saddle point. And then I don't know what happens. It's an open question. So, so in presence of the small external field, you have an effective action. The part involving the electromagnetic action is not modified because here we only consider the electromagnetic action of the generated field. And here, in the action of the fermions, we include the contribution of the external fields. Well, the theorem is that if the size of the external field in our space HDiv is small enough, and the smallness depends on our coefficient R already mentioned, then there exists a unique solution of the same min-max problem as before. Okay? But now, of course, in this min-max problem, we have inserted the external field in the definition of the action. The only difference is that we have taken a smaller domain here because we have perturbed our Lagrangian. Okay, so now the last thing we would like to know, once you have found a saddle point, you want to check that this saddle point satisfies certain Euler-Lagrange equations, and you want to check that these Euler-Lagrange equations are physically meaningful. So it turns out that the answer is yes, and but here we need an assumption, and in fact I don't know what happens if we don't put this assumption. It seems that in this case the functional is not of class C1, so one would have to be very careful. So we assume that 0 is not an eigenvalue of the operators dmja, and this is guaranteed in fact when you have these conditions. So assuming this, we are able to define charge density and a current density of the polarized vacuum, which are defined by the classical formulas, which are the following. You take QA, so what is QA? Well, it is a linear combination of the negative spectral projectors of our Dirac operator, and I remind you that only the case j equals 0 corresponds to the physical one. The others are just corrections. So you take the coefficient Cj, you take linear combinations of the negative spectral projectors with this coefficient Cj, and you get an operator QA, okay, which is a kind of renormalized one-body density for the Dirac C. Now you take the diagonal part of the integral kernel of QA, you take its trace C4, and you get ρA. For JA, you have to multiply QA by the matrices alpha 1, alpha 2, alpha 3, and you get the current density. Okay? Now, what we proved is that the operator, so assuming that 0 is not an eigenvalue, that the operators trace C4 of QA and trace C4 of alpha k QA are locally traced class, so that these objects are well defined, because when you have a locally traced class operator, you can define the diagonal part of its integral kernel rigorously. And so you have well-defined functions here, which are in L1 lock, and also which are in the Coulomb space of functions which can be considered as charge density with finite Coulomb energy. And so, by the way, this Coulomb space is going to be the dual of H dot, the space of functions with square integrable gradient. And so we have our charge and current density, and now we are ready to write the self-consistent equations, which are the Euler-Lagrange equations of our problem, and which are satisfied by our saddle points. So the saddle point A star satisfies these nonlinear equations, which are perfectly understandable. They just tell you that V star is the potential generated by the vacuum itself being generated by A star plus A external. That's exactly what we wanted to have. So it works for V star, it works for A star. Okay, so it's time for me to stop. So I just would like to mention, in fact, this is just the beginning. There are many open questions. I only talked about the vacuum, but can we add an additional electron? So can we extend this model to non-zero charge sectors and consider the interaction with the electromagnetic field? Can one prove that this min-max principle is global? I have no idea. Can one include the exchange term in this model? You see, there's something I've thrown under the carpet, which is usually when you write a mean field model, you have an exchange term. I just killed it in order to avoid complications. Can one study a time-dependent version of this model? The last question here is not even a question, because I'm really convinced it works. That is, you can study the charge renormalization associated with this ultraviolet cutoff in the same way as we did it in the electrostatic case. And this should give exactly the same formulas and results. Okay, thank you very much.
Thank you. Other questions or remarks? Yes.
You said that you killed the exchange term.
Yes.
Doesn't it destroy the gauge invariance?
No, because there is a way of looking at this model where you really don't see the exchange term. You see the exchange term when you start from no photon. Well, when you start from QED, not no photon, because now there are photons. When you start from the full QED Hamiltonian and try to make reduction by imposing that you are working with quasi-free states and so on. And then you get an exchange term. But there is another way of looking at it. From the very beginning, you decide that you only have a classical electromagnetic field. And that's a gauge invariant thing, okay? And you decide that coupled to this classical electromagnetic field, you have the electron-positron field, which is quantized. Now, when you do that, you really get a Hamiltonian which does not involve any exchange term, because you only see the electrons which do not interact. So electrons and positrons, in this view, they don't interact. They don't interact between them. They only interact with the electromagnetic field, which is classical. And in that case, they only see this one body. They only see this one body operator. And so there's no exchange term. And so passing to the mean field, you immediately get this without exchange terms. And in fact, in quantum field theory, that corresponds to what is called the effective action. I'm not an expert at all, but when they do functional integration, you can integrate first the fermionic variables, and you also get things like that without exchange.
You're using the term effective action. This is a standard term in quantum field theory, and this is precisely the same meaning that you.
Yes, I think so.
Okay.
But I am not an expert, but I really think so. It corresponds to integrating first the fermionic variables. And then you get a function of the electromagnetic field. But then, if you want to quantize this electromagnetic field, it's another story.
I have a question. I mean, you don't have the exchange term, but you don't have the full interaction between the electrons either, do you?
Yes, you have it.
It's a mean field picture that you are looking at.
Yeah, yes, it's a mean field picture, completely. Yes, yes. But now, when you don't have, the point is that you, well, in a way, what is really mean field is the electromagnetic field. That is, it's classical. Not mean field. What is not quantized is the electromagnetic field. It is a classical field.
You have no interaction between the particles, no?
Well, the particles interact with the electromagnetic field. Okay, that's where interaction takes place. Now, since they only interact with the electromagnetic field, then automatically, when you look for a minimizer of their energy, it is a Hartree-Fock state. Because they have no interaction between them. So given the electromagnetic field,
when you go in Coulomb gauge, you usually have this part, and you also have the direct.
That we don't have.
Yes.
We don't have, but you see, in the end, when you get the yes, that's completely true. But in the end, what you get, you get these equations. So it tells you that you get a mean field picture, exactly as you say. So, for instance, forget the magnetic field to write something with which we are more familiar, because there have been many works on that. So, if you forget the magnetic field but only keep the electric field, the equations you get are the reduced Hartree-Fock-Bogoliubov equation. That is no external term, but interaction between the electrons in the end. And mean field.
Are there more questions? I guess then we reconvene at 11 for Martin Königs's talk. Thank you very much.